cylindrical metal container, open at the top, is to have a capacity, fancy word for volume, 54 pi inches cubed. Inches cubed would be a good hint for volume as well, if you weren't sure what capacity means, how much it can hold. The cost of material used for the bottom is 50 cents per inch squared. The cost of material for the curved side is 25 cents per inch squared. Find the dimensions that will minimize the cost of the material. Okay. Perhaps a picture. So there's my cylinder. It's open at the top. I know the volume is 54 pi. And it's not given here, but usually they give you the volume of a cylinder. So pi r squared h. Hopefully you didn't need that to be given, because volume is the area of the base times the height. So let's see. Is that my primary equation or secondary equation? Is that the one I'm going to take a derivative of, or is that just going to be a helper along the way? That's going to be a helper, because I'm trying to minimize cost, so I need to write a cost equation. So secondary for that volume. Helpful maybe, but not what I'm trying to minimize. Okay, cost of that thing. Let's see, minimize the cost of the material. Well, there's two sort of separate costs. There's the bottom cost and the side cost. Okay, so the bottom cost is the area of the base times 50 cents. So 0.5 times pi r squared. That would be the cost of the denominator, of the bottom. Cost of the side is 25 cents times the area of the side. So I need the area of, like, that lateral surface area of a cylinder. Probably not given to you. But if you rolled out that cylinder, this would be the circumference, which is 2 pi r. That's why we want you to understand formulas rather than memorize them. That way when you see them later and you need them, you don't have to have them memorized. You can figure them out. So that surface area is 2 pi r h. Okay, that's my primary equation. That's what I want to take a derivative of, but not yet. Why not yet? What don't I like about this equation? Two variables, so that would be a real pain to deal with. But I've got a secondary equation I can use up here. 54 equals r squared h. Again, solve for either one, but this is another one where solving for one of the variables looks a whole lot easier than the other one. Avoid the square root thing. So h is 54 over r squared. So 0.5 pi r squared plus 0.25 times 2 pi r times 54 over r squared. So you still really haven't done any calculus yet. This is all algebra. I don't want to take a derivative yet because I got two r's in there. So 0.5 pi r squared plus, let's see, 0.25 times 2 would be 0.5. 0.5 times 54 would be 27. So 27 pi. In algebra, I would write it as 27 pi over r, right? Because the r over r squared. But in calculus, to make sure I take this derivative right, I'm going to write it as r to the negative 1. Alright, so now I can take a derivative. 2 times 0.5 is 1. That's kind of nice. So pi r minus 27 pi r to the negative 2. And we set that equal to 0. Right, because I don't know what this thing looks like, so who knows. But I do know that maxes and mins occur where c prime, where the derivative is 0. So let's take a derivative, set it equal to 0, and then we'll figure out if we've got a max or a min there. Pi r minus 27 pi over r squared. This is kind of like the one we just did. 27 pi over r squared equals pi r. Cancel the pi's. R cubed equals 27. That's convenient. So r is 3. But I really would like to know if that's a minimum or a maximum, right? You hate to do all this work and come up with the exact opposite of what you were hoping for. So there's 3. Let's check, almost wrote f prime. Let's check c prime at 2 and 4. So let's see, here's c prime right here. If I plug in 2, I get 2 pi minus 27 pi over 4. 27 over 4. What is that? 6 and some change. 2 minus 6 is negative. Remember, that's all I really care about. Plug in 4. I get 4 pi minus 27 pi over 16. Same thing. I don't know what 27 over 16 is, but it's less than 2. So 4 minus 2-ish is positive. So if c prime goes from negative to positive, then c has a minimum. Minimum of c at r equals 3. Okay. Which is what we thought, but now we've verified that. Find the dimensions that will minimize the cost of the material. Okay, r equals 3 inches. We're good there. H, how do I know what h is? Our secondary equation. H is 54 over r squared. So h is 6 inches. And then actually find the minimum cost. Well, I've got a formula for cost, so now I can just plug in the pieces. 0.5 times pi times 9 plus 0.25 times 2 pi 3 times 6. Plug it in r and h. And I'm just going to box that in and call it a day. I mean, clean it up if you want to. 4.5 pi plus, let's see, 6 times 6 is 36. A fourth of 36 is 9. 13.5 pi dollars, which is a weird answer, right? Like if you were actually doing this problem, you would multiply by pi to figure out how much this thing's going to cost. Yeah, these are the problems now where the calculus really wasn't too bad in that one. It was all the algebra and geometry that goes with it. Number 6, last example. An offshore well is located in the ocean at point W, 6 miles from the closest shore point A. on a straight shoreline. Shoreline, W is 6 miles away from point A. Okay, all that was the first sentence. The oil is to be piped to a shore point B that is 8 miles from point A. So shore point just means on the shore. So here's point B, 8 miles away. So I think I know where we're headed. I could pipe it straight to shore and then down the shoreline, or I could pipe it like all the way underwater from W to B, but I'm guessing it's going to land in between somewhere. The oil is to be piped to a shore point B that is 8 miles from point A by piping it on a straight line underwater from W to some shore point between A and B, and then on to B via a pipe along the shoreline. Okay, so we're going to go from here to there. Probably because it costs more to lay pipe underwater than it does to lay it on land. So the quickest or the shortest route would just be go straight from W to B, but that might be a costly route because it costs a lot of money to pipe underwater. If you want to save money on your underwater pipe, you could go straight to shore and then over, but that's like the most pipe you could use. So somewhere in between there is the money savingest route to go. Cost of laying pipe is $100,000 per mile underwater. So that'd be, this is $100,000 per mile. And $75,000 per mile over the land. So how far from point A should point P, oh, my 8's kind of in the way there, be located to minimize the cost of laying the pipe? So how far from A to P? So there's what we're looking for, is X. And what we want to minimize is cost. Okay. So it's another like two-part problem here. I got my underwater cost and my shore cost, I guess. So underwater is $100,000 times whatever that length is. So what is this length? Yeah, hypotenuse of x and 6. So that's the square root of x squared plus 6 squared. So I'm going to write that as x squared plus 36 to the 1/2, because I'm already thinking I'm probably going to need to do a derivative, and I don't want to do a derivative with square roots, so I'll put a 1/2 on that. The shore cost is $75,000 times whatever this length is. So how long is this piece? Well, be careful. This was x.
8 minus x.
8 minus x is this side over here. Okay, I think so. There's no primary secondary on this one. Like, that is the primary. It only has one variable. It's kind of annoying looking, but I think we're ready to take a derivative. Back up over here to the left to give myself some space. So 100,000 and then times 1/2 x squared plus 36 to the negative 1/2. But what else do I need to include? chain rule, good. So 2x on that. Plus, oh, maybe I should have distributed. I don't care what 8 times 75,000 is because it's a constant. So when I take its derivative, it doesn't matter. 75,000 times negative x. So that'd just be minus 75,000. Okay, cleanup crew over here. 2's cancel. So 100,000 with x in the top and square root of x squared plus 36 in the bottom minus 75,000. I switched back to square roots because now I'm back to doing algebra, and I'd rather a square root than an exponent. So exponents are great for calculus, square roots are better for algebra. Let's set that equal to 0. So how much can I do at once here? Move the 75,000 over and multiply by x squared plus 36. This is ugly. I'd really like to... Well, let's just wipe out the thousands to start with. Divide both sides by 1,000. I think then I would divide by 75. So not perfect, but reducible anyway. 4/3 x square root of x squared plus 36. What do you want to do next? Algebra all-stars. Square both sides. Let's see, that's 16x squared over 9 equals x squared plus 36. Our calculus is over. Now we're doing algebra. Let's see. Subtract x squared. Maybe multiply through by 9. One of the two. I'm going to have to multiply through by 9 eventually, so may as well do it now. Six times 9 is 54. Get rid of 5. Alright, we're almost there. 7x squared equals 324. X squared equals 324 over 7. Plus or minus square root of 324 over 7. But look at the picture. Look at the problem. Which one is it? The positive or the negative? Positive. Like if you go negative, then you're gonna pipe backwards and then go longer. Like the negative might be like a maximum, maybe. I don't know what the negative is, but we don't want the negative. That would not work. So there's our answer. I suppose we should check it, but I'm pretty sure that's going to be a minimum. Just from the context of the problem, it makes sense that if we piped it straight underwater the whole way, that'd be a lot of money. But if we went straight to shore and then along the shore, that'd be a lot of money. And so somewhere in the middle is our best shot for saving money. Alright, today's assignment is the last of worksheet 1, 10 through 13. Worksheet 1, 10 through 13.